what is called as the molar absolute humidity. You should know the terminology that is used in a particular. So when the basic equation is this is only for the 100% saturation. So whether you talk in terms of percent saturation or relative humidity, right? So it is 100%, both are the same meaning. Right? So this I can maybe put as sat. You should not confuse this with this. The pure component saturation pressure, this corresponds to the saturation condition, because the key point in humidification is we also talk about air-water mixtures which are not fully saturated. So that will lead to two definitions, two different degrees of measures of saturation. One is the relative humidity. So the relative humidity, we take the actual YW by YW saturation. This is the relative humidity. Even you express it in terms of clearly this will be less than 1, right? So if you're expressing it in terms of fraction, or you can multiply by 100 and express it as percentage. So the YW actual will lead to a capital YW actual, and this will lead to a capital YW saturation. That is the mole ratio. It is Y by 1 minus Y, mole fraction. Mole ratio is mole fraction by 1 minus mole fraction. Similarly, mole fraction is mole ratio by 1 plus mole ratio. Very easy to derive for binary mixtures. That's a standard terminology used, and even in extraction sometimes mole ratios are used. Right? So now you can define what is, I think, what Raoult calls as a percent saturation. Percent saturation is YW by YW sat. When you take the mole ratio actual to the saturation, you will get the percent saturation. That can also be expressed in terms of a fraction. So that you should know. And then we also saw that to bring an unsaturated mixture to saturation, there are many ways of doing it. Right? One is you just add more water. If you want to bring it to saturation, then you add water so that it becomes somehow, make the air-water mixture richer in water by somehow bringing it into contact with water for a longer time. And another way we saw is cooling. Because we have the temperature versus let's say YW, and it looks like this is the saturation. And then you have the, let's say, 70% saturation. So this is something with a relative humidity actually. Because I am plotting in terms of mole fraction. So if we want to bring it, you can look at the concept of due temperature, either in terms of the mole fraction or the mole ratio. So if I have a mixture which is at 70% saturation, right? So now to bring it to saturation, I can either follow this rule, add more, bring it to a longer time in contact with water, so that more water evaporates and it reaches saturation. Or the concept of dew point or dew temperature will be cooling the mixture to bring it to saturation. So that means the amount of water vapor or the mole fraction remains the same. That's why Raoult says out of contact with water. If I want to do that, let us say, then I have to cool the mixture and bring it to saturation. So this is the dew point of this mixture. That is the dew point temperature. That is the temperature to which I should cool the mixture at constant pressure out of contact with water, right, to bring it to saturation. So the same, the horizontal line. So this mixture, this is the dew temperature. You can also correspond, in fact, the calculation I did yesterday's prop with the dew temperature turns out to be approximately 25 degrees centigrade. We saw how to do that. So this now becomes the saturation. So I have to substitute that into this equation and find the temperature. Right? saturation. And you can do the same thing in terms of pressure. I wonder how this will probably be decreasing because YW is inversely proportional to. So it's very important. This is a constant pressure. Typically 1 atmosphere. This could be a constant temperature. The pressure will, you should know how to plot this. We've seen how these diagrams would look like. This is the inversely proportional, almost like a hyperbola. So you get a curve like this. Let's say this is 100% saturation. Now 80%, let's say relative humidity will look like this. It will be below again. You just have to mark off at each temperature. This distance, if I take 0.8, I get 80% relative humidity curve. Right? So I can get this, let's say this 80%. Now you can probably talk about the concept of a new pressure. Now I have a compress. So another same way, suppose let's say mixture is at 80% relative humidity. I can again bring it to saturation by bringing it into contact with water. That's the same procedure as this. But instead of, now this is a fixed temperature, I can compress the air-water mixture again out of contact with water and bring it to saturation. Raoult discusses all of these things. So even though we don't have a problem to discuss this, but this is certainly will correspond to the new pressure at which the mixture water will start condensing, as we saw. If I cool it further, again out of contact with water, right? Because I'm decreasing the temperature, then the humidity is decreasing and saturation cannot be further saturated. So it will condense, the excess water will condense out. Same phenomenon will happen here. So I can continue to cool, compress the mixture, and once it has reached saturation, it cannot hold any more water. So the excess water will start condensing out and the humidity will actually start decreasing. So these concepts should be very clear. Raoult is the best source for, you might have some worked out examples on it. If you just go through, you will understand. So notation, terminology, concept of beautiful unsaturation. Any of the other phase diagrams we haven't looked at, actually we always think of it as equilibrium, but in humidification, non-equilibrium or out of equilibrium conditions are very important and dealt with in Raoult. So this is the idea. The same equations apply. We just have to take the degree of unsaturation into account for doing the calculation. So you should be aware of it. So you cannot say the equilibrium thermodynamics will be restricted only to the saturation curve. You should also be aware of the relative humidity and percent saturation and how to generate those curves. So are there any questions on this?
The T ranges, temperature ranges are water vapor count when the heat increases outside. In summer, actually,
No, it's not water vapor outside. This is a special process used to measure the due temperature of the mixture. So if I have an air-water mixture and I want to bring it to saturation, so I cool the mixture, that's all.
but that the case in the nighttime rain should come, sir, right? In the summer, daytime the moisture is high, the nighttime temperature is low, so that the should rain, sir.
No, but it does not reach the 100% saturation. Not necessarily. It has to cool sufficiently. So that means if the temperature is not cool enough. We say it's raining, we say it's 100% relative humidity, it is condensing out. Right? So if it is not raining, then it does not reach 100% saturation. That's what I can say. Cooling is not enough. It has to reach the due temperature. Right? Then it has not reached, that's what I can say. Yes, any other question? Okay, then we'll move on to the other problem, more important for vapor equilibrium. There are some problems, most of them are standard applications of the algorithms we have already discussed. But I just want to point out, let's say we take one or two problems and illustrate the algorithm. If we take problem 5, there is a somewhat unusual specification which we haven't looked at. This is from YBC, I think, very standard problems. So what we say is N20 1, that's called component 1 in FT. find that out and then move on to the new temperature or bubble temperature calculation. So what he says is, one, if you see, determine the vapor and liquid compositions with an unusual specification, and Raoult usually valid only for a binary mixture at this point at all. At 70 degrees centigrade, 600 torr, that is 600 with a new unit that you should be aware. So here, because Antoine's equation gives it in terms of this, normally it's convenient to use this and not Pascal and bar and all that. But you should know how to convert it. Standard is 760 torr. 1 torr is 1 mm Hg. Right? So 760, you know, all of you know that it's 1 atmosphere. So you can easily convert the bar, atmosphere, whatever, Pascal, whatever you want. Right? So this, if you see, this specification we haven't encountered because it's not one of the standard specifications. But we saw the number of degrees of freedom for a two-phase. If we make this 2, the number of degrees of freedom is C. So we looked at 4 different specifications. In each one of it, C minus 1 will be the mole fraction. The other one is either temperature or pressure is specified. So we get the 4 combinations: liquid or vapor, temperature or pressure. Now we specify temperature and pressure. Then I run into an awkward situation of having to specify only C minus 2. So neither the vapor nor the liquid will be fully specific. So this is not normally encountered. But however, because for C equal to 2, this degree of freedom will be 2. So I can talk of specifying the temperature and pressure and it will be completely specific. In no other case will just the specification of temperature and pressure be sufficient to determine the other degree. So binary 2 degrees of freedom, so this is a perfectly valid specification. Calculation for ideal is what you are asked to use. 5 and 6 using Raoult's law. So very easy to do it. Dy1 is P1 sat x1, dy2 x2 is 1 minus x1. So if I just add it, I get P1 sat x1 plus P2 sat and 1 minus x1. So normally this is used to find the bubble pressure, but here pressure is given, temperature is given, so I can easily find x1, and so then I can find y1 also. And so this is somewhat unusual, but the calculation is very straightforward if you are just using ideal VA. So that is what I wanted to say. Now let's take up the next one. Find T and Y1. So we take the problem T, find T. Find T and Y1 when P is equal to 600 torr and x1 is equal to 0.4. So this is clearly a bubble temperature calculation which we saw even for the ideal case requires an iterative solution. So let's do 1 or 2 steps of the iteration. So the Antoine's equations are given. So n pentate, we have log 10 V, which is in mm mercury, is given by A 6.87632 minus B is 1175.78 divided by T, which is in degrees centigrade. That's very important now to keep in mind. And the C is 233.205, and the same thing for N. Heptane is what is given. I have log 10. 0.89 6.89 36 minus 1264.37. given. And so what is the first step in the algorithm? We choose the algorithm where the ratios of the saturation pressure come into play. We also look at the other algorithm which we discussed right at the beginning. So what is the first step in calculating bubble temperature? You have to choose a temperature, right? So T naught, we said good choice would be, I could ask you to choose the temperature accordingly, in a particular way, right? In an exam, for instance, I could say choose so that it is the weighted average of the boiling points, right? So it could be, since X is given, with X1, TBB1, boiling point, and of course 600 dot plus X2 plus 600 dot, how would you find the boiling points? From the substitute. So this is typically used to calculate the saturation pressure given the temperature, but if I substitute 600, I will get TBB1. Right? If I substitute 600 here, I get, if you know the advanced equation can also be used to get the pure component boiling points given the pressure. Given the temperature, you calculate what is called as the saturation pressure. So the answer, I'm just not going to wait for you to give, the answer I'm getting is X1 is 0.4 times the answer I have is 29.3, this is in degrees centigrade, plus X2 is 0.6 times what I have here, you can check it. This is what I am getting. And if you put 600, you should get 29.3. And if I put 600 in this, I should get 90. So these are the pure component boiling temperatures. So when pentane and heptane, those are available to you. So you cannot say that the information is not given. If you know how to calculate it from the algorithm. Answer I'm getting 66.1 degrees centigrade. So that is what you have to do. So now to calculate the next one, you have to construct the algorithm. Right? So the key point here, to get this reconstruction, and the key point is first apply to get the formula, apply the modification constraint to on Y, because that's not known. So I get P equal to P1 sat. I'll just do it for now the key idea is to divide by a certain saturation pressure. We chose PC sat, so I can choose P2 sat. So if I divide, I get the ratio. I have only one ratio to deal with here. So, and then I have to invert it. So this is P1 sat by P2 sat of T x1 plus 1 minus x1. So this is P over P2 sat. So what I need is an equation for P2 sat in terms of temperature. That's what I will use to find the next temperature, a successive temperature. So P2 sat, if I just invert this and take P over P times 1 over P1 sat by P2 sat of T. So if I want, I can put this as Pj plus 1, and this would be Pj, right? x1 plus x1 is given, so I can actually do that. So this is x1 is 0.4. All those are given, right? So this times 0.4 plus 0.6. This is the formula equal to. So if I want T1, right? Maybe we can. First thing I have to now do is to calculate degree centigrade. Because this is in logarithm to the base 10. So let's see if we can calculate it correctly. So P1 sand at T0 in all we use mmHg. P1 sand and P2 sand. That's what I need to substitute, right? Into this equation. P is 600. So can you calculate? At 66 point, that is arbitrary 66.1, but we have chosen it to be that. So what is P1 sand at 66.1? If you calculate right hand side and take 10 raised to the power of that. In this you make a mistake. You all what is it? 1914. Okay, 1914 is what I have. 1940.52. And P2 sand, what I have is 264.25. Right? So I need to go and substitute that here. Now you will see the difference, how this will work as an integrated procedure. So P2 sand at T0. So first one, we calculate is 600 times 1 over 0.4 times or 1914.52 divided by 64.25 plus 0.6. So can you tell me how much would that be? That is easy to calculate. What is the answer? That should be easy to calculate. 600 times this. So however easy and trivial it is, you still have to do the calculation and get the correct answer. Yes? 171.52. So you can clearly see what we need to compare is 264 versus, that is what I chose for P2 sand. That is at T0. But what I am getting, the new value of P2 sand to be 171, whatever, right? So that means that T1 may be different from T0, clearly. Now I need to use this to calculate T1. Right? So for that I need to invert this. So I need to invert only this. Right? So I get log 10 PC sand, P2 sand, right, is this. So minus 6.89386 is, or rather 6.895, I will put it over here. So this is the other equation that I should have ready, is 1264.37 by T plus 216.64. So now I need to invert this. So T plus 216.64 is 1264.37 divided by 6.89386 minus log 10 to the base P2 sand. And so T would be this minus 216.64. This is what I have to use to calculate T1 now. So obviously for P2 sand, you put 171, I have to take the log of that, 171.52. So what is the answer you get now? This will be T1. 64.71. You have to continue this. It's very easy for me to set it up on the calculator on an Excel sheet, and you can simply redo it. And now what you have to do is I will get T1. T2 sat of T1 I already have 171.5. So I substitute that and then I get T2 sat of T2, which I have calculated to be 157.14 T2 sat. Now what I will get is not this, but something else. So I have to now calculate T1 sat and T2 sat. So if I do that, right, so what I have at 54.71, so T1 now becomes, T1 is 54.71. So I need to calculate T1 sat and T2 sat. And T1 sat 54.71 is 1379.97. And of course this is T2 sat is 171.52. If I do this, then I get an answer which is 157.14. You can see all the way from 264.25 come down to 170 because it's progressively decreasing. 171 and I come to 157.14 T2 sat, which would imply that T2 is actually equal to 52.51. We have to see that there is clearly a progressive convergence. So we start with the initial guess, which is T0, and T1 will come to 54.71, and T2 is 52. Clearly it is not yet there. There are still iterations to be done, but it is at least monotonically decreasing, so you expect it to converge in maybe a couple of more iterations. You can carry it out and see. But on the other hand, if you look at, for instance, the other algorithm that we use, where we don't impose a mole fraction constant, but simply calculate y1 and y2, right? So let us take that, right? So that I will do here. So we start here again with T0 equal to 66.1. Right? Let me do that here. Confusion. So there, if you recall, that algorithm involved directly calculating y1 and see whether the mole fraction constant is satisfied or not. Right? So let's do that once. So with that, T1 sat and T2 sat. So I'll calculate y1. Y1 is T1 sat x1 by b, and 1914.52 times 0.4 by 600. And I'm getting already, you can see y1 itself is base is 603 times, and 0.4 will be greater than 1. So you know that this is how we find out that y2, obviously I don't take 1 minus y1, but y2 I have to calculate independently. That will be 264.25 times 0.6 by 600, and that is 0.26425. So now what you do is clearly y1 plus y2 is greater than 1, is 1.54. And so now the question is what, whether we should increase or decrease the temperature. So clearly we should decrease the temperature. That's what we saw. Because if the y's are becoming greater than 1, means I have chosen a higher temperature, so I need to decrease it. So I can use this itself, and the algorithm accordingly becomes T0 divided by 1.54. So that turns out to be 42.91. So now I am calculating T1 sat and T2 sat at 42.91 degrees centigrade. And then if I do that, then what I am getting is, if you do now, at this y1 turns out to be 0.637 and y2 turns out to be 0.105. Now it has become less than 1. So I will increase the temperature. And T2 then can be shown to be equal to 57.81 degrees centigrade. So it's sort of oscillating, as you can see. And you can easily check the convergence rate. Carry out with one problem is sufficient for you to do it. So the due temperature is going to be very similar to this, right? So bottle temperature, you have two algorithms. What I expect you to do, at least to complete a few more iterations and see which one is converging So that would be a good exercise for you to do. But basically the algorithms are already being discussed. All you should know is how to apply it in this case. Yes?
Currently substitute that this P-side equation in P1 dot plus equal to P1 x1, P-side x1 plus P2 side 1 minus x1.
And move on.
And find the temperature.
You mean to say you can do it directly, you are saying? Yeah, possibly you can do that. P is given. You have only one equation in T1 you are saying, and so you can, yeah, you have to get the T. Might be I don't know what type of equation you will get. You can try that. You can solve it. What he is saying is that you use this equation P is given. X1 is given. So you have only one equation and one unknown. You can do that. You can see what type of an equation you get. Right? This is, you have to substitute all of this into this and see whether you get a decent equation for T. Then you can directly do it. That's true. You can try that. So this is a general algorithm that will work in then you have to see what to manipulate it and get an equation for T. Right? You can try doing that also. So you have a single equation in T1. You can directly do it, but this will not work for the due temperature problem. I don't know, you can try that. For due temperature, whether you can do a similar thing, you get a single equation in T. Right? So you try that and do it. But this is the application of the algorithm that we discussed. And check whether if it turns out to be non-linear equation, then again you need to do an iterative procedure. Because you have this T in the denominator. And so we don't know. If it turns out to be quadratic, then maybe you can directly solve it. Right? So you have to figure out what type of an equation it will look like. You can certainly try it and do it. That will give you an idea what the temperature is. So bubble due temperature, x1 would be given. Obviously we have to use the other sort of equation. And maybe that you can check. That also will give a straightforward single equation solution. And you can certainly try that, and if you can get an explicit expression, then there's nothing like that. Are there any questions, further questions? And in fact, this may even work for the modified Raoult law also. As long as the X is specified, you can easily get that. So it might not work in all cases, right? So another option is for due temperature to see whether the same idea would work. But when you go to modified Raoult law, some of these special procedures may not work, and so on. So you have to be aware of that. Are there any further questions? Okay, if not, what I will do is move to the modified Raoult law. So what I want to take is there are several standard models that are given, van law and the modulus 2 suffix and 3 suffix. And basically van law and 3 suffix are the most common used in textbooks because they are easy for computation and they are not so familiar like the 2 suffix modulus equation. So what I am going to take is the problem A, because the point to note with the modified Raoult law is what are the parameters that we have to. Suppose let's say you choose the van law model, it has 2 parameters A and B. Or if you choose the 3 suffix modulus, you have 2 parameters A12 and A21. So some books use the difference, they use A and B for 3 suffix modulus also, that's probably from Sandler. So the the question is, how are you going to determine the parameters? Let's say you take a particular example, ethanol, benzene. Mixture, or any mixture you want, ethanol, water, ethanol, water. Determining the parameters, you need a limited amount of experimental data. Otherwise, you cannot. That's one of the limitations of these models, because we don't know how to determine the parameters unless you have some PEV data. So the utility of these models, you have limited PEV data, use that to calculate the parameters. Right? Basically, a certain fitting is done to calculate the parameters from the PEV data, and when you use the parameters to extrapolate and get the PEV calculations done outside the range for which temperature is, for which data is not available. Right? Here, what I'm going to do is consider a simple procedure. We're just using the fact that the system has an azeotrope, because these data is very well known. So it simplifies the calculation of the parameters. Another way, you have to do some curve fitting. Right? So basically, we'll see how to do it in the simplest case, where we're just using data at one point to calculate the parameters. So now we take ethanol, benzene. And we are given, but if you look at Ravi's data, he gives the azeotrope at 1 atmosphere for a whole range of systems which exhibit azeotrope at 1 atmosphere. So here we are given that this exhibits an azeotrope at T equal to 1 atmosphere, T equal to 68.24 degrees centigrade, and X1 is 0.44. So what is Y1? Also 0.44. That's not given, but this is the, you should know first what an azeotrope is. Otherwise, you cannot even proceed one step. And so, what we use is the modified Raoult's law. The modified Raoult's law says Py1 is for binary mixture, P1 SAN of T gamma 1 X1, and Py2 is P2 SAN of T gamma 2 X2. So now I'm going to apply these equations at the azeotrope. If I apply this, so y1 is equal to x1 and y2 is obviously equal to x2. Y2 is just 1 minus y1. At the azeotrope, the mole fraction simply cancel out. And so, I have P equal to this and P equal to this. So I have P1 SAN. This is of course at the azeotropic temperature. That's very important to keep in mind. Times gamma 2. So what I get is actually a value for the ratio gamma 1 to gamma 2. This is P2 SAN at T azeotrope by P1 SAN at T azeotrope. So what do we do with this? Now we have to choose a particular. So let's calculate for the ethanol. You are given also the Antoine's parameters, ethanol and benzene. Right? So ethanol is supposed to be component number 1. And so what I have to do is calculate P1 SAN at 68.24 and P2 SAN at 68.24 degrees centigrade. In fact, we don't even need the ratio, we can directly get gamma 1. So that's what we need actually. So P by P1 SAN. Because P is also given, P is equal. And gamma 2 would be, we can actually get not just a ratio, but we can directly get the activity coefficient. So I can calculate this I've calculated it to be 503.61. Sand is 519.75. And so I can get gamma 1 to be P azeotrope is 1 atmosphere, so 760 by 503.61. And gamma 2 is 760 by 519.7. You can see that both of these, whatever the value is, it's got to be greater than 1. Gamma 1 is 1.509 and gamma 2 is 1.462. So first thing you should know that this is what is referred to as a positive deviation from ideality. It's not given here, it only says it's an azeotrope. It's not given there is a minimum boiling. You have to know now what type of an azeotrope it is. So calculations you don't need to know, but constructing the phase diagram is useful to know whether this is now going to, by just looking at the values of gamma, you can say whether this is going to exhibit a minimum boiling or a maximum boiling. Positive deviation, minimum boiling azeotrope. You should also know what minimum boiling means. Minimum boiling means that at the given pressure, if I plot the Txy diagram, because that's very important. What this minimum boiling azeotrope means is that if I plot T versus X and T versus Y, both of them will have a minimum. That's what is a term used for minimum boiling. So it will look like this. Exact values you can calculate, but minimum will occur at the same point. That's very important. So this is T, this is clearly T versus Y, and this is T versus X. So you can now plot. In fact, if I want to really plot it properly, this is actually 0.4 it says, so this is sort of shifted a bit. But anyway, we'll assume it is 0.4. This temperature is what is given to be 68.24. Now we don't know which one is greater, but you can easily calculate for ethanol, right? Again, the pure component boiling points can be calculated from the Antoine's equation, from the same equation that's given. So what we need is that 760 mm. What is it? For ethanol it is, so we have plotted this mole fraction of ethanol. We know this is 1 ethanol, and the boiling point is 78.3. This is 78.3. This is slightly higher. This is the boiling point of benzene is 18.1. What is interesting to know is that if I now construct a phase diagram at constant temperature, namely the azeotropic temperature, the pressure versus X and the pressure versus Y curve will actually exhibit a maximum at the azeotropic pressure. There is a correlation between it. Can be theoretically prove. For instance, it can be theoretically proved that both the temperature curves, T versus X and T versus Y, will, if the one undergoes a minimum, at some point the other will also undergo a minimum at the same point. That is the azeotropic point. Right? So X1 becomes equal to Y1. That can be established here. So at T equal to 68.24, if I were to plot the pressure versus X, so I have X and Y here. The pressure, it is easy to show, if it is constructed, it is easy to show that the of course I have the saturation pressure values here. So if I now plot mole fraction of ethanol, X1 or Y1, this is the ethanol. So pure component ethanol, we know what the saturation pressure is at 16.24, it is 503, right? So I will have to mark 503.61. You can just see from another way of, even without don't have the gamma, right? If I just know the pure component values of the boiling points, clearly I can verify whether it's at minimum boiling or maximum boiling, because this I can calculate just for pure component properties from the Android equation. And I have given that the azeotrope is at 68.2, so clearly you can infer it is not going to go up or come down. That is, I don't know if there are cases where you can have both maximum and minimum, but these are typical cases. So clearly this is 80 and this is 70. It has to be a minimum boiling only. It cannot be a maximum boiling. That's another way of verifying. So now you can see the pressure is 1 atmosphere, both of these are lower than 1 atmosphere, so automatically you can infer the pressure versus the run out of time. So if I were to plot this would be 519.7 feet above, and then here P versus X will be on top. So P versus X will have something like this, and the P versus Y will have maybe a form like this. And the azeotrope point will be perfect matching. This is 0.4, and this would be clearly 760. So you can sort of roughly construct these curves, how they qualitatively they are going to look. This is now very important because, for instance, if I want to calculate the dew temperature, right? It depends. It might give a good idea as to what values you should choose as the initial by looking at where your mole fraction is. Because you can easily do some calculations here to find out the bubble pressures, because this will involve calculating the bubble pressure, and the bubble pressure we know explicit expression is there. For instance, if we want to construct this diagram, T equals 68.24. So temperature is fixed. I can either choose to calculate the bubble pressure or the dew pressure. Obviously, I will choose the bubble pressure, because once I choose the bubble pressure, the dew pressure calculation is automatically taken care of. Because here I have a choice. If I want to simply construct the curve, right, then I choose the bubble pressure. Because the bubble pressure, I also get the Y value. So with that, I can construct the dew pressure also, right? So we'll see how to construct these curves. And of course, if I come here, the dew temperature, bubble temperature, I may have to carry out an iterative procedure to find out what the temperatures are, right? So we'll see how to construct those curves quantitatively in tomorrow's class.